Okay, let's take a look at number 17 from chapter 9. A solution of potassium nitrate and the solid precipitated silver phosphate are formed when aqueous solutions of silver nitrate and potassium phosphate are mixed. So here's the precipitated silver phosphate. There's yellow precipitate. And so this is going to be different than your test, because your test I'm not going to give you the product, so you're going to have to figure out the product. And so your test would be more like predict the reaction when solutions of silver nitrate and potassium phosphate are mixed. And so, was there a specific question, or did you just want me to go through the?
Yeah, I just wanted to see how you came to the answer, because I don't want to see the answer.
Well, this one I would do, you would be given silver nitrate. So the first thing is you have to get the formula for silver nitrate correct. What is the formula for silver nitrate? Yeah, AgNO3. And then potassium phosphate. What's the formula for that? K3PO4 is correct. So how you predict the products? They gave it to us, but we would predict it using the AB plus CD type pattern. The AB plus CD type pattern we're going to form, well, this is silver and phosphate, so it's going to form silver phosphate. Silver phosphate has a formula. And then we're going to have potassium with nitrate. Potassium nitrate is KNO3. So that would be our silver phosphate and potassium nitrate. Then we look if there's a driving force present. Is there a driving force present? And so first thing is we look at silver phosphate. Is that a precipitate, or is that, if it's a precipitate, it's solid. So is it a solid, liquid, gas, or aqueous? Solid. Yeah, all phosphates are insoluble. And so it's a solid. It's not soluble, it won't dissolve. So silver phosphate, which is the yellow solid there, is going to precipitate out. Potassium nitrate. Is that a precipitate? Solid, liquid, gas, or aqueous? Aqueous. So silver nitrate. Potassium nitrate is aqueous, silver nitrate is aqueous. All nitrate salts are soluble. All potassium salts are soluble. Phosphate salts are insoluble except for group 1 and ammonium. But silver is not a group 1 and ammonium. And so we have a driving force. We say driving force is precipitate of silver phosphate. Now we'll want to balance it. So how should we balance it? Yeah, we'll need 3 AgNO3s, 3 silvers, 3 silvers. That gives us 3 nitrates, 3 KNO3s, and then it's balanced. Okay, after you do this, then what's the next step? Well, this is done if we're only asking for the CE. So the next step is to do the IE. The IE, some people have rules for the IE. IE, you dissociate or break apart. If we were to summarize it, we break apart the soluble salts. The lattice gets broken apart there. And strong acids. Everything else we pretty much leave alone. There is one thing with the strong bases. Hydrolyte. These species are called the strong electrolytes. We break apart the strong electrolyte. Electrolytes are these salt solutions. the ions, electrolytes. So silver nitrate, do we leave that alone or break it apart? When it breaks apart, what does it break up into? Yeah. And nitrate ions, yep. The main thing is we just finished balancing it, so we don't want to screw up the balance. So we're going to maintain that balance. There are going to be 3 silver ions and 3 nitrate ions. Potassium phosphate. Does water break apart potassium phosphate crystals? Yeah, it breaks it up into and phosphate ion. The potassium is a, gotta make sure, it's a +1, so we need 3 potassiums for every phosphate. How about silver phosphate? Do we break that apart? No, it's insoluble, it's a strong lattice, so water's not gonna tear it apart. Potassium nitrate? Potassium nitrate's a weak lattice. The only way to get potassium and nitrate to precipitate out of solution is to evaporate all the water. If you evaporate all the water, then you're going to force the potassium ions together with the nitrate ions. So we're going to make sure everything's still balanced. It is. Okay, what's the next step? We determine the, what? We go to the NIE and we determine that by eliminating the, yeah, so what are the spectators? Nitrate, nothing happens there. Potassium, nothing happens there. The only ions that react are the silver ions. Silver ions like phosphate ions. Silver ions like phosphate ions will come together to form a precipitate of silver phosphate solid. So that would be the NIE for this. Okay, is that good? Okay, other questions? Uh-huh.
Can you do number 27?
Number 27. Number 27, I was thinking about this problem because there are multiple ways you can answer this problem. When it's oxidized, it depends on how completely it is oxidized. For example, when methane is oxidized, what's produced? Well, it depends. You know, sometimes soot is produced. Sometimes carbon monoxide is produced. Sometimes carbon dioxide is produced. So this question is not very clear. And so what they should have done to make this question better is they should have said is completely oxidized. If they said is completely oxidized, then we know it goes to carbon deoxide, carbon trioxide, tetraoxide, carbon dioxide. How do you know it's carbon dioxide for complete oxidation? Because we talked about it. I think we talked about it a bunch of times, but do you remember? This is the partial oxidation alcohol. If you take a look in your bodies, you consume ethanol. You know, it's ethanol. We'll ignore these ones here, these two ones. But ethanol is oxidized, but it's incompletely oxidized. Ethanol becomes oxidized and forms another organic compound. It's called acetaldehyde. Acetaldehyde is so it's partially oxidized. And then acetaldehyde is again partially oxidized to acetic acid. And then acetic acid is further oxidized, and let's see if we have a more complete. Where does it eventually end up? Well, acetic acid gets introduced into another metabolic pathway. Of course, we don't want to drink. You don't want to drink this. You don't want to drink this, right? It's bad, but methanol would be oxidized in your body. It's going to form formic acid eventually, not acetic acid. Acetic acid is okay because it's survival. So we go to acetaldehyde, acetic acid. There's some steps in here that I'm missing. You don't want to drink antifreeze. Antifreeze, did you know antifreeze is an alcohol too? You know, automobile antifreeze. You don't want to drink this stuff because the way it's metabolized can cause you trouble. Form calcium oxalate. Oxalates are poisonous to some problems, but ethanol's okay. Eventually, ethanol is going to be oxidized all the way to the end, which would be carbon dioxide. And so if you drink alcohol, eventually that alcohol is going to be oxidized all the way to carbon dioxide. In that process, you've extracted the maximum amount of energy you're going to get from that alcohol. And you can't further oxidize carbon dioxide. And so what do they mean by this, you know? So did I talk about turning wine into vinegar? Did I talk about that?
The cheap bottle of wine?
The cheap bottle of wine I got in Joshua Tree. This was a long time ago. Does anybody remember that? Maybe I said it last month. You don't? No. Okay, I went camping in Joshua Tree once. And I went into town, and into the town of Yucca Valley. And there's a dollar store there. And at the dollar store, they had 99-cent bottles of Santa Barbara wine. Santa Barbara wine. You know, I just drove in from Santa Barbara, Joshua Tree. It's like 4 hours. But I gotta buy that 99-cent bottle of Santa Barbara wine. So get it back to the campfire. Took one sip of it and spit it out. And it turned out that 99 cents was the total waste. Should have saved it because it was a bottle of vinegar. And so basically what happened was that ethanol was partially oxidized to acetic acid. And so it tastes like vinegar. It was bad. Unfortunately, it would have been okay if it was completely oxidized to CO2. Then I would have had sparkling grape juice, which I would have been okay with. You know, sparkling grape juice, I'll accept that. But vinegar, no. And so, anyway, it was good. It wasn't a complete waste because you used that bottle of wine to put out the fire. That was okay. Anyway, getting back to the original question, so we have to make an assumption. The assumption is that it's completely oxidized, just like for all combustion reactions. For all combustion reactions, it doesn't matter if it's ethanol, it doesn't matter if it's sugar, it doesn't matter if it's whatever. We're always going to assume it's completely oxidized to CO2. And so when we do combustion reactions, the products are going to be CO2 and water, although they might not be. It might not be depending on the conditions. You know, a little bit of air leaks in through the cork of a wine bottle, it'll lead to partial oxidation. You know. They have cases of this stuff there. You know. But let's go back to the question. Where's the sun gauge go? Did I close it by accident? I must have. Anyway, it was the oxidation of ethanol is what it is. So what is the formula for ethanol? There are different ways of writing ethanol's formula. CH3, CH2, OH. This is what we call the condensed structural formula. And this is typically how it's written in organic chemistry. The OH is the this. What we can do is we can further condense this. If we take this first part and condense it down, then we have 2 carbons and 5 hydrogens. And so we'll take this 2 carbons, 5 hydrogens, and then add the OH. The OH is called the alcohol group. And we can further condense this down if we want it. If we further condense it down, we'll get C2H6O. But when we have C2H6O, it's hard to tell if that's an alcohol or some other compound, because there's something called isomers. Have you ever heard of isomers? If you recall, what are isotopes? Isotopes are the same element, different amounts of neutrons. Well, isomers are this. Same molecular formula, different structure. And so there are 2 common chemicals with this formula. One is ethanol, the other is dimethyl ether. Dimethyl ether, you don't want to drink that stuff, cause problems. So here we have ethanol, which is liquid, and then we're going to oxidize it. Well, what are we going to do? Are we going to partially oxidize it or completely oxidize it? Completely. In organic chemistry, if you're going into organic chemistry, then you'll have a whole slew of oxidizing agents that you'll use. You'll use mild oxidizers and harsh oxidizers. Or you'll use harsh oxidizers at very low concentration to get the reaction that you want. And so in organic chemistry, you play around with the conditions and the oxidizers to accomplish what you want. This is something your bodies do, essentially. And so when we combust it, what do we react it with? O2. O2, this is redox. This is oxidation reduction. Oxidizers, the word oxidizer comes from oxygen. Oxygen is the original oxidizer that chemists use. It's abundant, plentiful. Although there are more powerful oxidizers that have been discovered, oxygen's cheap. Oxygen's cheap because it's free, essentially. It's in the air we breathe. So it's cheap. Of course, our bodies use this, so if we consume ethanol, we also have to inhale some oxygen, otherwise we're not going to get any reaction. So this is going to form CO2 and H2O. Now when we balance it, we balance the carbons first. So 2 carbons will need 2 CO2s. 6 hydrogens will need 3 waters. That will give us 6 hydrogens. Now the oxygen, the only oxygen I want to change, I don't want to change this, I don't want to change this or this. So everything's balanced. The only one I want to change is this one. And so I have 1 oxygen over here, one oxygen plus X times 2 oxygens is equal to, I have 2 oxygens here plus 3 oxygens. Oh no, is that right? Yeah, no, 4 oxygens, sorry, 4 oxygens plus 3 oxygens. So I got 1 plus 2x is equal to 7. And therefore x is equal to 3. So 3. Okay, then we need the states. Oxygen is a gas, CO2 is a gas. What is water? A liquid. And so that's the reaction for the complete, the alcohol and alcoholic beverages. So this is why I had to give this a second thought. I thought, maybe I'm not going to assign this, because normally when the alcohol and alcoholic beverages is oxidized, it doesn't go all the way to CO2. It goes to something like, it might go to acetaldehyde. Acetaldehyde is nasty. Do you know what they preserve specimens in biolab in? Starts with an F. Formaldehyde. Formaldehyde is also known as methanol. There's a 1-carbon aldehyde. Acetaldehyde is a 2-carbon. It smells like formaldehyde. It's nasty stuff. But it has the aldehyde. These are the classic compounds called the aldehydes, which are stinky. And so when ethanol is oxidized, it could form formaldehyde, could form acetic acid, vinegar. For sure my wine was vinegar. Okay, other questions? Any questions on some of the earlier stuff? I had a lot of questions this morning, so I didn't make it that far. Okay.
I have a question. Number 55.
Nitric acid appears to dissolve solid lead 2 hydroxide. It doesn't appear, it dissolves. But when we have the process of dissolving something, there are 2 ways things can dissolve. One is a physical process. Like, for example, dissolving sugar in water. That's a physical process because what you make is sugar water. However, if you try to dissolve gold in water, does it dissolve? No. And in fact, you can get it to dissolve in not regular water, you can get it to dissolve in royal water. Have you heard of royal water? Royal water is given the Latin name aqua regia. Did I talk about that? Yeah. And so, but when you dissolve it in royal water, it's not a physical process because what you don't get is gold water. What you get are gold ions in water. Gold ions are quite a bit different than gold metal. In order to get the gold metal back, you'll have to do another chemical reaction to get the gold metal back. So that's called a chemical dissolution process. And so this would be a chemical. So this is why they put dissolve in parentheses, not parentheses, in quotation here, because this is a chemical dissolving process. We aren't going to get our lead hydroxide in water. We're going to end up with something totally different in water. And so what is it? So in other words, nitric acid will react with solid 2 lead hydroxide. So what is nitric acid, the formula? when I look at something like HNO3, what is it? What chemical property stands out about HNO3? HNO3 is a strong acid. That's one chemical property that stands out about HNO3, but there's another chemical property that stands out about HNO3. What is it? Not only is it a strong acid, it's also a strong,
Well, the nitrogen is not very happy because there's a positive byproduct.
yeah, nitrogen's pretty unhappy in this. It has a positive 5 charge, which means it's a strong oxidizer. And so two things that really stand out about nitric acid: one, it's a strong acid; two, it's a strong oxidizer. Its metathesis properties do not stand out because all group 1 salts are soluble, including hydrogen, and all nitrate salts are soluble. And so, you know, as far as redox is interesting, acid base is interesting, metathesis is uninteresting. But this is a metathesis reaction here. So it's nitric acid plus PbOH2. So for these types of things, you know, let's just follow the pattern, the AB plus CD pattern. See what we get. So here we are going to get hydrogen and hydroxide. Hydrogen hydroxide forms H2O. And here we're going to get lead 2 nitrate. What's the formula for lead 2 nitrate? Okay, H2O is a solid, liquid, gas, or aqueous? Liquid. PbNO3, all nitrate salts are soluble, means it's aqueous. So if we look at this, this is solid because hydroxides are insoluble, except for, hydroxides are insoluble except for which one?
Group 1, group 2.
No, not all of group 2.
Oh.
Not all of group 2.
Group 1, ammonium, and calcium.
Yeah, group 1, ammonium, and
Calcium, barium.
yeah, calcium, strontium, barium. So that means, like, say for example, it has a big impact. One of the impacts is this. Sodium hydroxide, is it a strong base? Sodium hydroxide, strong base? Sodium hydroxide is a strong base, actually. Magnesium hydroxide, strong base? Well, this is a hydroxide, so are hydroxide strong bases? You guys remember from the base chart? Yeah. You see hydroxides here? Down here, strong base, strong base. Sodium hydroxide, strong base? Yes. Potassium hydroxide, strong base? Yeah. Rubidium hydroxide, strong base? Yes. Lithium hydroxide, strong base? Ammonium hydroxide, strong base? Yeah. Calcium hydroxide, strong base? Yeah. Strontium hydroxide, strong base. Barium hydroxide, strong base. Magnesium hydroxide, strong base. No. Magnesium hydroxide. Copper 2 hydroxide, strong base. No. Iron 3 hydroxide, strong base. No. Zinc hydroxide, strong base. No. Those are not strong bases. So what's the difference? Well, the difference is this. The strong bases are soluble hydroxides. The weak bases are insoluble hydroxides. So people eat magnesium hydroxide, but you would not want to eat calcium hydroxide. Even though you need magnesium and calcium, you don't want to eat calcium hydroxide because calcium hydroxide is a strong base, magnesium hydroxide is a weak base. And so if you ran out of magnesium hydroxide, milk of magnesia, don't substitute calcium hydroxide for it because calcium hydroxide is considered a strong base. Why? Because calcium hydroxide is soluble, magnesium hydroxide is insoluble, so it helps protect you from the full force of hydroxide. Anyway, let's go back to this here. And so lead 2 hydroxide is not considered a strong base. Lead 2 hydroxide is considered a weak base. You know, it's got hydroxide, but that hydroxide is locked up in the crystal lattice. It's not free to attack acids. This one doubles. This could be an acid base, you know, hydroxide and nitric acid, or it could be a metathesis that doubles. But is there a driving force for this? Because, you know, this is a solid, everything else is aqueous. So if I look in the reverse direction, it looks like the driving force is in the reverse direction. It looks like the driving force is in the reverse direction because if I go backwards here, I'm going to form a precipitate, a PPT. But in the forward direction, I don't form any precipitate because this is not a precipitate, this is not a precipitate. And so here I'm essentially getting rid of one precipitate for no precipitates. Is that good? No, it's bad. We'd say that there's no driving force, but are we done with driving forces? No, we got to look for precipitate, and we have to look for gas formation, and we have to look for, yeah, it doesn't have to be a strong acid, it just has to be stronger. So you could start off with a weak acid, you just have to end up with a weaker acid. But in this case, we're starting off with a strong acid, so this is going to be, well, we don't know if it's stronger because there could be an even stronger acid. And so what we choose to say is acid. And so that's the acid in the forward direction. What's the acid in the reverse direction? Water. And so which one's the stronger acid, nitric acid or water? Nitric acid. In this one you shouldn't even have to use the chart. Would you rather have a cup or a glass? A glass of nitric acid or a glass of water? A glass of water. And so we have driving force. All we need is one driving force. So even though this precipitate thing screws us up, it's okay. We'll just have this as our driving force. We just need one thing. And so this question could confuse a lot of people because they're thinking there's no driving force because we're dissolving a precipitate, not forming a precipitate. We want to form precipitates, right? But anyway, we have to balance it. How should we balance it? We've got to balance this. We have one hydrogen here and two hydrogens. I'd like to balance by ions. And so rather than calling this one oxygen, two oxygens, one hydrogen, two hydrogens, rather than doing that, I look at this as two hydroxides. And then I look at nitrate. I don't consider this one nitrogen, three oxygens. I just consider the whole thing as a whole, as a nitrate. This we can do in metathesis because metathesis, the ions just get rearranged. And so we don't have to break it down per atom. For combustion, we break it down per atom. So over here, I look at this differently. I consider this 2 carbons, 6 hydrogens, 1 oxygen. 6 oxygens here, etc. For metathesis, 1 nitrate here, but I have how many nitrates there? 2, so I'm going to have to multiply this by 2. And then I have 1 lead here, 1 lead, that's okay. I have 2 hydroxides here and 2 hydrogens here. So 2 hydrogens and 2 hydroxides are going to make how many waters? one way of thinking about a water is HOH. And so each water contains one hydrogen, one hydroxide, in a way of thinking, you know, even though it's not correct, technically, but it's easier for balancing. So we'll need two hydroxides, therefore I'll need two waters. Then it's balanced, and we call this the CE, and then what comes after the CE? The IE. Nitric acid, does water break it apart? Into how many H pluses? And how many nitrates? Does water break apart the lead 2 hydroxide precipitate? No. So we leave that. Does water break apart water into hydrogen ions and hydroxide ions? No. We're going to leave that alone. Not to any significant extent. It can break it up into a little bit, but this is what gives water its pH. Water gets its pH because in a billion, if you have a billion water molecules, about 4 of them actually can break up and react. It's so little. Lead 2 nitrate, does that break apart? Yeah. Into lead and 2 nitrates. Look, any spectators here? Yeah, nitrates. Nothing happens to those. Eliminate it. So NIE is just going to be the 2 H pluses are going to attack our lead 2 hydroxide solid. And this is going to break apart that lattice to form lead 2 ions. So it's the hydrogen ions. The hydrogen ions are going to help break apart that lattice by reacting with the hydroxide ions. And in the process of forming stable water molecules. Okay, other questions? No other questions? If there are more questions, you can ask me today or tomorrow. What we're going to do next is we're going to start chapter 10. Chapter 10 is not going to be on this next test. And so this next test, the test on Thursday, is just going to cover up through chapter 9. Chapter 10 deals with the topic stoichiometry. Stoichiometry. Stoichiometry is what we call quantity relationships. And the quantity relationships are going to be in different forms. So let's look at the combustion of methane as an example here. Methane's a gas. When we look at it, if I have 1 mole of methane, how many moles of O2 am I going to need to combust it? And how many moles of CO2 will form? And how many moles of water will form? So CO2 is a gas, O2 is a gas. So when we do this, we can look at the mole ratio. Mole ratio. And so this is the quantity in terms of moles. Well, first, in order to get the mole ratio, we have to balance this. So what do we need to balance it? We have 1 carbon here, 1 carbon here, 4 hydrogens, which means we need 2 waters here. That gives us 4 hydrogens. And this is going to be 2 times 2 oxygens plus 2 oxygens, 4 oxygens. So we need just 2 O2s here. And then it's balanced. And so the mole ratio is 1 mole of methane, 2 moles of O2, 1 mole of CO2, and 2 moles of water. This is the mole ratio. Okay, so these are the quantity relationships here. So if I have 2 moles of methane, then I gotta double everything. 2 moles of methane, we're gonna require 4 moles of O2. It's gonna produce 2 moles of CO2 and 4 moles of water. But moles are a little bit abstract because moles are, Avogadro's numbers worth of molecules. So it's just a huge number of molecules. And so sometimes what we'll do in terms of quantity relationship is we'll look at the mass ratio. In terms of the mass ratio, a mole of carbon, on average weighs 12.01 U. And 4 moles of hydrogen, well, each mole of hydrogen is 101, so it's going to be 404. And so 1 mole of methane molecules is going to weigh 16.05 grams on average. Do you know the average mass of oxygen? What is the average mass of oxygen? Well, each oxygen is 16.00. We have 2 of them, that's 32, and then we have 2 of these molecules, so it's going to give us 64.00 grams. And so if I have 16 grams of methane, I need 64 grams of oxygen. How many grams of CO2 are produced? Well, carbon's 1201, oxygen is 16, so it's 44.01 grams. And how many grams of water? Water is 18.02 on average grams per mole. So this is going to be 36.04 grams. And so this would be the mass ratio. A mass ratio is inconvenient though, because it's much more convenient to write the mole ratio or the molecule ratio or the particle ratio. The mass ratio we wouldn't write in here. It's a lot less convenient. But these are quantities. And so we call this the stoichiometric ratios here. These are stoichiometric ratios. Stoichiometric means it's just the right amounts. And so these are the stoichiometric mole ratios or mole amounts. This is the stoichiometric mass ratios or mass amounts. And so the next thing we're going to look at is a typical stoichiometry calculation. Because do we have a mole meter, something that measures how many moles of, let's say I wanted to figure out how many moles of methane I have. Is there a meter that has that? Where I can just measure how many moles of methane? Like at the gas pump, if you're at the gas pump at the gasoline station, it's measuring out how many gallons of gas you're getting. But is there like some kind of pump where you can measure how many moles of methane you're getting? No, there isn't. How about mass meter? And there is a mass meter. Do you know what the mass meter is called? A balance, yeah. A mass meter would be a balance. And so let's take a look at a typical stoichiometry. A simple one would just be in moles, if you have 1.5 moles of methane, you're going to need how many moles of O2? Double that, so it's 3. But moles is a bit tricky. Mass is a lot easier. And so in a typical stoichiometry problem, what we do is this. We know the mole. So if we have moles of anything, A, we can relate that to moles of B. B can be anything. And so here it could be, moles of A could be methane, moles of B could be oxygen, or CO2, or water, anything. And so this is the heart of the stoichiometry map, because at the heart we have the stoichiometric ratio. Stoichiometric ratio between A and B. But since we don't actually measure the moles, we measure things like the grams. And so typically we'll start off with mass of A and then convert it into moles. To go from grams of A to moles of A, we need the molar mass. I'm going to flip it over upside down. And then we end up with moles here, but moles are still abstract. It's hard to visualize that. And so we're going to go from moles of B to mass of B. That's mass of B. Here. And here we're going to use the molar mass. And so let's do a typical stoichiometry calculation here. This typical stoichiometry calculation is going to look like this. We'll take methane, CH4, and O2. And this is going to produce CO2 and water. And so the example, let's just say, for every pound of CH4 combusted, how many pounds of CO2 is produced? So for this problem, we'll just start off. We need the balanced chemical equation. So those 2 here and 2 there. 1 to 2, 1 to 2 ratio. And then we're going to go into the stoichiometry math by starting off with pounds of methane. From pounds of methane, we can't. Do you know the molar mass of methane in terms of pounds per mole? No. We know the molar mass of methane in terms of grams per mole. So from pounds, we're going to go to grams of methane. And so we go to grams of methane. And then from grams of methane, we're going to go to moles of methane. Here. And then from moles of methane, well, we know the mole ratio. It's just a 1-to-1 mole ratio. We're going to go to moles of CO2. And from moles of CO2, we're going to go to grams of CO2. And from grams of CO2, we'll go to pounds of CO2. So we can figure out this. And so let's give this a shot here. This is going to be dimensional analysis in doing this particular problem. So let's try some dimensional analysis here. We're going to start off with 1 pound of CH4. 1 pound of CH4. And then we need to get rid of the pounds. So we're going to go from pounds to what? Yeah. And so it's going to be 453.6 grams for every pound. And so the pounds cancel. This tells us I have 453.6 grams of CH4. Now where do I go? Yeah, so I'm going to go to moles. And so 1 mole of CH4 molecules weighs 16.05 grams. And so the grams of CH4 cancel, and that leaves us with how many moles of CH4 I have. Okay, and then from moles of CH4, we can relate that to moles of CO2. For every mole of CH4, I'm going to form 1 mole of CO2. So 1 mole of CO2 for every 1 mole of CH4. And so moles of CH4 cancels, that gives us moles of CO2. Okay, then we're going to go to grams of CO2. I calculated this earlier. There's going to be 44.01 grams of CO2 for every mole of CO2. It's a molar mass. So moles of CO2 cancel, and then finally we'll go to pounds. So they're 453.6 grams for every pound of anything. So just the grams cancel there. That leaves us with pounds of CO2. Okay, we can do some further simplification. For example, the 453.6 in the denominator there cancels the 453.6 in the numerator here. And so essentially it's just going to be 4401 divided by 1605 in this one. 44.01 divided by 16.05. Yeah, how many 6 figures am I allowed? Yeah. So we'll go 2.7420. pound of CO2. Almost 3 pounds, 2 3/4. So we can say for every pound of methane, we're going to generate about 3 pounds of CO2. Okay, this one? The next problem is going to be advanced. How many pounds of air is required or are required to burn 1 pound of methane of CH4? So how many pounds of air are required? Well, do you see air in the equation? There's no air in the equation, but there's oxygen. And where do we buy the oxygen, or do we get it for free? For free. We get it for free from air. But it's not really free because the air is going to lose that oxygen. So to figure out how many pounds of air use the oxygen. So we need additional data. Air is about what percentage oxygen? About what percentage of air is oxygen? Nitrogen, about 80% nitrogen. Air is about 80% nitrogen, about air consists mostly of 2 gases, nitrogen and so if it's 80% nitrogen, it's going to be about 20% oxygen. But the problem with that percentage is that's percentage by mole. It's not percentage by mass. You know, so if I had 100 moles of air, I'd have 20 moles of oxygen. But what if I had 100 pounds of air? Would I have 20 pounds of oxygen? No. It's different. The mole percentage, the mole fraction, or the mole ratios are different than the mass ratio, mass fraction. And so we'd have to calculate it. But, you know, calculating it would be a standard question in Chem 1A, but calculating it in Chem 4 would be too much. We're not going to calculate it. Instead, I'm going to look it up. I already looked it up, but it seems to have misplaced it. This is by mole. Volume and mole percentage are the same. I'm not going to use it. This looks like percentage by mass. No, this is by mole. Do you see? It's by mole. I don't want that. This is a percentage by mass here. We'll assume this person did this calculation correctly. But you gotta watch out. Yahoo Answers is bad. But we'll just say assume air consists of 23.1% oxygen by mass. It's actually a pretty straightforward calculation. But it means that this question's order. All right. So this is going to be another stoichiometry problem. We're going to start off with 1 pound of methane and 1 pound of CH4. And then where do we want to go? We're going to go from pounds of methane. Actually, we can map this out. Maybe we should do that first. If we map it out, it's CH4 plus 2 O2s yields CO2 plus 2 H2O. Okay, I'm not going to write the states in. So we have pounds of methane. We're going to go to grams of methane. From grams of methane, we're going to go to moles of methane. From moles of methane, we're going to go to moles of oxygen. Here we see it's a 1-to-2 ratio or 2-to-1 ratio. For moles of oxygen, this is pure oxygen, right? This is not moles of air. This is moles of pure oxygen. We're going to go to grams of oxygen. This is pure oxygen. From grams of pure oxygen, we're going to go to grams of air. Okay, so let's set up the dimensional analysis equation here. So setting it up, we're going to have 1 pound of CH4. And then we're going to convert it to grams. So we know that there are 453.6 grams for every pound of anything. The pounds cancel, that leaves us with grams of methane. And then from grams of methane, we'll go to moles. So we know that 1 mole of methane molecules weighs 16.04 grams. So grams of methane cancel, that leaves us with moles of methane. And then we're going to go to moles of O2, because for every mole of methane combusted, we're going to get 2 moles of O2. 2 moles of O2 for every 1 mole of methane. And then from moles of O2, we'll go to grams of O2. There are 32.00 grams of O2 for every mole of O2. So moles of O2 canceled. That leaves us with grams of O2. If we have pure oxygen, let's say we went out, rather than using air, air is free. What if we went out and bought a bottle of oxygen? If we bought a bottle of oxygen, then this is where we stop. Stop here. This is how many grams of O2 we need up to here. But we don't want O2. We want to go with the free stuff. And if you want the free stuff, then we're going to have to figure out how many grams of air we want. And so what's the last conversion factor?
The 23.1 grams of oxygen is how many grams there?
Yeah. Good. And so there are 23.1 grams of O2 for every 100 grams of air. And so the grams of O2 cancel, and that leaves us with grams of air. So let's go ahead and do this calculation here. I don't wanna stop at grams, where do I wanna go to? Pounds. In fact, you know what, I shouldn't have stopped at grams here. Let me, because there are different ways I could do this, sorry, let me change this a little bit. I'm going to, I'm not gonna use that factor. This is in grams. Normally we stop at grams because most people work with grams, but now we're working in pounds. And so I'm gonna add one more thing here. I'm gonna go from grams to pounds. And so 1 pound is equivalent to 453.6 grams. So the grams cancel. And what this is gonna give me is it's gonna give me pounds of O2. So 2 doesn't cancel. And so I'd stop here, and if I stop here, that takes me to pounds of pure O2 required. And so let's figure out how many pounds of pure O2 are required. And so the 453.6 is canceled as well, so that's going to give me 2 times 32, 2 times 32 divided by 1604. And so the pounds of O2 required is 3.990 pounds. So I need about 4 pounds of O2. But do I have pure O2? I don't have pure O2. I have air. So if I need 4 pounds of pure O2, how many pounds of air is required? And so this is the last step here. And the last step is this. For every 100 pounds of air, how many pounds of O2 are there? It's a mass percentage. 23.1. And so it doesn't matter if I do this in pounds, grams, or whatever, the ratio should be the same. And so the pounds of O2 cancels and leaves me with pounds of air. So this is going to be times 100 divided by 23.1, which gives me 17.272 pounds of air. In 17.272 pounds of air, I'm going to have 3.990 pounds of O2. And the 3.990 pounds of O2 is required to react with every pound of methane. And so, in terms of pound ratio, it would be 1 pound of methane requires about 4 pounds of O2. It would be 1 to 4 mass ratio. In terms of mole ratio, it's a 1 to 2 mole ratio. All right, well, we're going to stop here. We'll take a break and then we'll continue this.